Welcome. Today we're diving into the essential concepts of machine learning model tuning. Whether you're just starting out or looking to refine your skills, understanding how to balance model complexity, prevent overfitting, and optimize performance is crucial. We'll explore real-world scenarios, practical techniques, and the underlying theory that drives robust machine learning solutions. Let's begin our journey by examining what overfitting looks like and why it matters for your model. Overfitting happens when a model learns not just the patterns in your training data, but also the random noise. This means the model performs exceptionally well on the training set but struggles to generalize to new unseen data. Imagine a student who memorizes answers instead of understanding concepts. They ace practice tests but stumble on the real exam. Overfitting is a common pitfall, especially with complex models or small datasets. A loss curve. Overfitting is easy to spot. As training progresses, the training loss keeps decreasing, showing the model is fitting the training data better and better. However, the validation loss, which measures performance on unseen data, stops improving and starts to rise. This divergence signals that the model is starting to memorize noise instead of learning useful patterns. Recognizing this pattern early helps you take corrective action. Underfitting is the opposite problem. Here, the model is too simple to capture the underlying structure of the data. It's like using a straight line to fit a complex curve. No matter how hard you try, the model just can't keep up. You'll notice high loss on both the training and validation sets, and the model fails to perform well on any data. This usually means you need a more complex model or better features. Diagnosing underfitting involves looking at your model's performance on both training and validation sets. If both losses are high and the model isn't improving with more training, it's a clear sign of underfitting. This often happens when the model lacks the capacity to learn complex relationships in the data. Solutions include increasing model complexity, adding more features, or reducing regularization. Bias variance trade-off is a core concept in machine learning. Bias refers to errors from overly simplistic models that miss important patterns, leading to underfitting. Variance, on the other hand, is the error from models that are too sensitive to small fluctuations in the training data, leading to overfitting. The goal is to find a sweet spot where both bias and variance are balanced, minimizing total error. Balancing bias and variance is all about model selection and tuning. If you decrease bias by making your model more complex, you risk increasing variance. Conversely, simplifying your model reduces variance but increases bias. The art of machine learning is finding the right balance for your specific dataset and problem, often through experimentation and validation. Regularization is a technique used to prevent models from becoming overly complex and overfitting the training data. By adding a penalty term to the loss function, regularization discourages large weights and helps the model generalize better. It's a crucial tool in the machine learning toolbox, especially when working with high-dimensional data or powerful models. L1 regularization, also known as lasso, adds a penalty proportional to the absolute values of the model's weights. This has the effect of pushing some weights exactly to zero, effectively performing feature selection. Lasso is especially useful when you suspect that only a few features are truly important for your prediction task. L2 regularization, or RIDGE, adds a penalty based on the squared values of the model's weights. Unlike L1, it doesn't force weights to zero but shrinks them towards zero. This spreads importance across all features and is especially helpful when many features contribute a little to the outcome. Ridge regularization is a go-to for controlling model complexity without dropping features entirely. Elastic net regularization combines both L1 and L2 penalties. It's especially effective when you have groups of correlated features. While Lasso might pick just one feature from a group, Elastic Net can retain the whole group, maintaining both sparsity and group selection. This makes it a flexible and powerful choice for many real-world datasets. It's important to distinguish between model parameters and hyperparameters. Model parameters like weights and biases are learned automatically from the training data. Hyperparameters, on the other hand, are set by the engineer before training begins. Think learning rate, tree depth, or the number of neighbors in KNN. Tuning hyperparameters is key to getting the best performance from your model. Grid search is a brute force approach to hyperparameter tuning. It evaluates every possible combination of hyperparameters within a predefined grid. While it's guaranteed to find the best configuration in the grid, it can be highly inefficient, especially with many parameters or large search spaces. Grid search is best for small, well-defined problems. Random search takes a different approach. Instead of checking every combination, it randomly samples hyperparameter values from a distribution. This method is much faster and often finds a good configuration in less time, especially when some parameters have little impact on performance. Random search is a practical choice for large or complex models. Bayesian optimization is a smarter way to tune hyperparameters. It builds a probabilistic model of the objective function, often using a Gaussian process, to predict which hyperparameter sets will perform best. By balancing exploration of new areas and exploitation of known good regions, Bayesian optimization can find optimal configurations with fewer evaluations. Early stopping is a regularization technique used during iterative training. It monitors the model's performance on a validation set after each epoch. If the validation performance stops improving for a set number of iterations, training is halted. This prevents the model from overfitting and saves the best weights, making it a simple yet powerful tool. End-to-end machine learning pipeline automates the entire workflow, from data ingestion and preprocessing to feature engineering, model training, and evaluation. By chaining these steps together, you ensure consistency and reproducibility. Pipelines are essential for scaling machine learning solutions and preventing errors like training serving skew. Encapsulating your workflow inside a scikit-learn pipeline object offers major benefits. It prevents data leakage by ensuring that transformations like scaling are applied only to the training folds during cross-validation, not the entire dataset. This leads to more reliable model evaluation and better generalization in production. Training serving skew refers to a mismatch between a model's performance during training and its performance in production. This can be caused by changes in data distribution over time, differences in preprocessing code, or using features during training that aren't available in production. Addressing skew is critical for reliable deployment. Several factors can cause training serving skew. Data drift, where the distribution of incoming data changes over time, is a common culprit. Using different preprocessing steps in training and production, or relying on features that aren't available in real time, can also lead to skew. Monitoring and aligning your pipelines is essential. To manage data drift, set up statistical monitoring to alert you when production data diverges from training data. Techniques like the Kolmogorov-Smirnov test or population stability index can help. Automated retraining loops that update your model with fresh production data ensure your model stays relevant and accurate. Target leakage through time occurs when future information is used to predict past events. This can lead to unrealistically high performance during training but poor results in production. Preventing this requires a strict chronological split, only using features available before the target event occurred. This is especially important for time-dependent datasets. To avoid target leakage, always split your data chronologically when working with time series or temporal datasets. Make sure your training features only include information available before the outcome. This simple step ensures your model's performance is realistic and transferable to real-world scenarios. Ensemble learning combines the predictions of multiple models to create a stronger, more robust learner. The main strategies are bagging, which reduces variance by averaging predictions like random forest, and boosting, which reduces bias by focusing on errors like gradient boosting. Ensembles often outperform individual models. Bagging and boosting are two popular ensemble methods. Bagging, such as random forest, builds multiple models in parallel and averages their predictions to reduce variance. Boosting, like gradient boosting, builds models sequentially, each one correcting the errors of the previous, reducing bias. Both approaches can dramatically improve model performance. When your target classes are highly imbalanced, standard training can lead to poor results. Downsampling removes instances from the majority class, while upsampling replicates or synthetically generates minority class examples. Techniques like SMOTE create synthetic data points to balance the classes, improving model fairness and accuracy. While SMOTE can help balance classes, it's not without risks. If the minority class contains noisy or outlier data, SMOTE may generate synthetic points in the wrong regions, creating unrealistic decision boundaries. This can increase false positives in production, so always validate your synthetic data and monitor performance closely. Feature engineering is the art of transforming raw data into meaningful inputs for your model. This might involve extracting new features, combining variables, or encoding categorical data. Well-engineered features can reveal hidden patterns and dramatically boost model performance. Feature selection is about choosing the most predictive features and removing those that are redundant or noisy. This speeds up training, reduces overfitting, and improves interpretability. Good feature selection ensures your model focuses on what matters most, making it more robust and easier to understand. While feature engineering creates new variables to help the model, feature selection filters out unnecessary ones. Both are essential for building high-performing models. Think of engineering as expanding your toolkit and selection as choosing the right tools for the job. Filter methods evaluate features based on their statistical properties independent of the model. Techniques like correlation matrices, chi-square tests, or ANOVA help identify which features are most relevant. Filter methods are fast and scalable, making them a great first step in the feature selection process. Wrapper methods use a machine learning model to evaluate feature subsets. By adding or removing features and checking model performance, these methods can find highly predictive combinations. While more accurate than filter methods, wrappers are computationally expensive and best used when you have time and resources. Filter methods are quick and independent of the model, while wrapper methods are slower but often more accurate. The choice depends on your dataset size, computational resources, and the importance of feature interactions. Many practitioners use filters for initial screening, then wrappers for fine-tuning. Covariate shift occurs when the distribution of input features changes between training and real-world test data. If your model performs well on validation but poorly on new data, it likely overfit to the training distribution. Addressing covariate shift requires collecting more representative data and robust validation strategies. If your model excels on the validation set but fails on new, real-world data, covariate shift is a likely culprit. This means your validation set was too similar to your training data. To diagnose, compare feature distributions across datasets and use domain knowledge to ensure your data is truly representative. To combat covariate shift, gather diverse data that reflects real-world scenarios, demographics, and environments. Use stratified sampling and robust cross-validation techniques to ensure your model sees a wide range of cases during training. This helps your model generalize and perform well in production. We've covered the most important concepts in model tuning, from overfitting and underfitting to regularization, pipelines, and handling imbalanced data. Remember, the key to successful machine learning is balancing complexity, monitoring performance, and continuously validating your models with real-world data. Apply these concepts in your projects by starting with simple models, tuning hyperparameters, and using pipelines for automation. Monitor for overfitting and underfitting, and always validate your results on fresh, representative data. These steps will help you build robust, reliable machine learning solutions. Machine learning is an iterative process. As new data arrives or requirements change, revisit your models, retrain, and refine. Set up monitoring and automated retraining to keep your solutions up to date. Continuous improvement is the hallmark of successful machine learning in production. Building great machine learning systems is a team effort. Collaborate with domain experts, data engineers, and stakeholders to ensure your models solve real problems and deliver value. Open communication and shared understanding lead to better outcomes for everyone involved. The field of machine learning is always evolving. Stay curious, keep learning, and experiment with new techniques. Whether it's trying out a new regularization method or exploring advanced ensemble strategies, ongoing curiosity will keep your skills sharp and your models competitive. Modern machine learning libraries like scikit-learn, TensorFlow, and PyTorch provide powerful tools for building, tuning, and deploying models. Take advantage of built-in pipelines, hyperparameter search, and monitoring features to streamline your workflow and focus on solving business problems. As you build machine learning models, always consider ethics and fairness. Monitor for bias in your data and predictions, and strive for transparency in your workflows. Responsible AI ensures your solutions are not only effective but also trustworthy and fair to all users. The future of machine learning includes advances in automation, explainability, and integration with other technologies. Stay informed about new developments such as AutoML, interpretable models, and edge deployment to keep your skills and solutions ahead of the curve. Thanks for joining this deep dive into machine learning, model tuning, and best practices. By mastering these concepts, you'll be well equipped to build models that are accurate, reliable, and ready for real-world challenges. Keep experimenting, learning, and pushing the boundaries of what's possible with machine learning.